Let's talk about bonds. Alright, so what you should know at the end of this PowerPoint is to be able to determine what type of bond is formed between any two elements and have the basic knowledge between the three types of bonds, which will technically break into four types because the one breaks into two different types at the end. Alright, so quick review of things we need to talk about in this one. We need to know what valence electrons are. Those are the electrons that participate in chemical bonding, the ones that are available in the outermost shell of an electron. So the inner ones are not available for bonding, but the outer ones are available. That's why they're called the valence electrons. Every element wants to achieve a full outer energy level. Those usually have 8 electrons in it, which is why we call it an octet. The one exception being like one's near helium, so hydrogen only wants to have 2. Okay, so our chemical bonds, there are 3 main types. Ionic, which is generally between a metal and nonmetal. Make sure you know that. Covalent, they're cooperating between 2 nonmetals. And metallic are between, surprisingly, 2 metals. So ionic bonds are between a metal and nonmetal, we just said. When the elements bond, the electrons are transferred. So the metal gives up its electron, it gives it over to the nonmetal, and they actually lose the electron completely in this ionic bond process. Examples here are any metal on the left side of the periodic table and any nonmetal on the right side. So sodium chloride, lithium oxide, magnesium chloride, etc., etc. All these have a metal and a nonmetal in them, therefore each of them make a ion, a positive ion for the metal. These are all positive ions formed. And then these all make negative ions. When those ions are formed, they make ionic bonds. So we note here, sodium is going to lose an electron. If you lose your negativity, you become more positive. And it's going to transfer it to chlorine. So now chlorine's got 1, 2, 3, 4, 5, 6, 7, and that 8th one it'll get from sodium, so it's got a full octet. And sodium had just 1 valence electron out here. It's going to lose it when it gives it to chlorine, so it's got a full octet in the innermost shell. They're both happy having a full octet, so that's what makes this sodium-chlorine bond. Now technically, there's a bunch of sodiums and chlorines bonded next to each other all around, making this sodium chloride or a salt cube. That's why salt comes in large cubes. Same like thing you'll have like salt crystals if you were to eat it at the dinner table. So ionic crystals always, or ionic bonds always happen between in crystal form in a large amount of atoms. It's not just 2 of them, even though it's how we usually show it in chemistry. Okay, then we're talking about this joke. So the name's bond, ionic bond. They're taken, not shared. If you find it funny, awesome. If not, well, hopefully you get it. That was my cat. Okay, covalent bonds. They're between 2 nonmetals. So when the elements are bonded, the electrons have to share the electrons because both of them want more electrons. Neither one's going to want to give up an electron to do this process. So this is where it breaks down to 2 different types. We can have polar covalent bonds where they don't share the electrons equally, or we can have nonpolar covalent bonds and they do share them equally or pretty close. Examples here are phosphorus and chlorine, so PCl3. Phosphorus trichloride is what it technically is, but we'll get into the naming a little bit later. All of these compounds down here are all nonmetals. So you look at all these elements, they're all to the right of that staircase, they're all nonmetals. That tells you it's a covalent bond. Oh, go back. Okay. So if we look here, in a covalent bond you've got 2 hydrogen atoms. They each have just 1 electron in their valence shell. Technically hydrogen just has just 1 total. When they bond together, these 2 electrons are going to circle around and orbit both of the hydrogen atoms. They're going to share those 2 electrons, so they have a full octet, even though it's only 2 for hydrogen. But they have the noble gas configuration of helium, which makes them happy. Just like a noble gas, they're good to go. Same thing for fluorine. They've got 2, 4, 6 here, a 7th one, but they both want to have 8. So to get 8, they have to share this unpaired electron set. These two are paired, paired, paired. This one's not. This one's not. So they'll come together to make a bond by sharing these two. Now you can count 2, 4, 6, 8 here. 2, 4, 6, 8 here. They both have an octet, so therefore they're good to go. They're stable. We'll skip this third one for just a second. Come down to the one where we've got 4 fluorines and 1 carbon. So carbon's got these orange ones, 1, 2, 3, 4 valence electrons. And so it's missing 4 electrons to make its octet, and fluorine, each fluorine's got 2, 4, 6, 7. So it needs 1 more. Each fluorine's going to come in and bond with one of chlorine's atoms. Now this fluorine's got 8. This fluorine's going to come in and make a bond to make 8. Same thing with the one on the right and the one on the bottom. When chlorine does that, it's bonding with 1, 2, 3, 4 separate fluorine atoms, giving it a total of 8 as well. So it's got a full octet. It's also content. They all have a noble gas configuration. That's why CF4 is a stable molecule. You can do the same thing in a weird way when you've got 2 oxygens and 1 carbon, where here this carbon and its 2 electrons over here and 2 over here bond with 2 different electrons from oxygen on the right and 2 on the left. This is called a double bond. We'll go into more detail about how you know this can happen in the future, but it can happen as well even though they're not making one single unpaired electron like all the other 3. It'll make a double bond to make CO2 or carbon dioxide that we normally breathe. Pull it up if you want to see the molecule carbon tetrafluoride. Then our last type, metallic bonds. So metallic bonds, surprisingly, are between 2 metals. These are a little bit weird because the electrons are shared between metals, but it's not in the same way that covalent bonds are. The metals don't hold on to or share or spend time with one atom having the electron sometime and another one having it the other times. It's not like custody of children. It's more like they have a sea of electrons. The electrons just kind of flow around and have this weird little dance going around where the electrons are just floating between all the nuclei and they have no standard place they have to be. They have to have the right number of protons and electrons making up to make it neutral, but they don't stick any one set place. That's why they're so malleable and can move around. Examples, any 2 metals together. Sodium, magnesium, sodium and francium, lithium and copper, take your pick. Alright, quick review on chemical bonds and electronegativity, why this is important. So electronegativity is the ability or the strength of an atom to draw electrons to itself. Now this usually occurs when it's happening in bonding. They're technically assigned values to each element based on experimental and predicted bond energies. In the past, we just said if it's the general trend, if it's going to increase or decrease comparing 2 atoms. Now we're going to actually look at the actual values of how strong an atom's electronegativity is to compare and see what type of bond it actually is. Mostly we're looking at polar covalent, but technically all of them. Okay, so fluorine, we should know from before, if you remember, is the most electronegative atom. It's got a value of 3.98. It really wants those electrons. It's got a really strong pull on them. And francium is the lowest at 0.7. It really doesn't want more electrons. It's whatever. Okay, so this is an electronegativity chart. You get something like this or numbers given to you on quizzes or tests when you need to use this to solve for the bond types. So here, fluorine's here at the red. It rounded 1 decimal place, so it gives 4.0 instead of 3.98. Francium down here at 0.7. So we see in general it trends up towards this way, getting bigger as you go up, smaller as you go down, and bigger as you go from left to right in general. So why is fluorine the most electronegative? Why not chlorine or bromine or iodine? They've all got 7 electrons. They're all just 1 electron away from a noble gas configuration. Well, remember, if I can get my face out of the way. There we go. Remember that when you go down a column, we're adding electron energy levels. So it's like a 1s, 2s, 3s, 4s. every electron energy level you add is making the atom bigger. And the electron out here on the end, out here, high little electron, versus the one out here, high little electron, is way farther away from the nucleus down here. So that distance increases, means those positive protons in the nucleus aren't going to be able to pull as strongly on the electrons, therefore decreasing the electronegativity of that atom. So that's why if you look at HF versus HCl, the distance between this electron here being pulled to the center, or this one here being pulled to the center, this electron is much closer to the protons in the center here than this electron is, because it's got a whole other energy level in HCl than there is in HF. So fluorine's got a much higher electronegativity than chlorine does. Right, so nonpolar covalent bonds. Electrons are equally shared during bonding. They spend equal amount of times on each atom in a nonpolar covalent bond. There's always going to be a non-metal bonded to a non-metal. This is because there's a very little or no difference in electronegativities. So 0 to 0.5, we'll give you numbers in a little bit. So a little nonpolar cartoon to show you. Here's examples of when you're sharing something, in this case like ice cream. If you share it equally and one of you is not scarfing down 3 of the 4 pieces of the ice cream cone, if it's shared equally, that'd be an example of sharing it equally being a nonpolar covalent bond. Okay, then if we look at polar covalent, the second type, this means they're being shared, but they're not being shared equally. So electrons, one atom's getting the electrons more often than the other one. So it's still a non-metal bond to a non-metal, but there is a difference in electronegativity. It's more than 0.5. So in a nonpolar bond, these electrons are right in the middle between each chlorine atom. They have the exact same electronegativities. But in HCl, chlorine's got a higher electronegativity than hydrogen does. So the electrons are closer to chlorine. They spend more time over here. Chlorine's got more of a pull, more of the control of the electrons than hydrogen does. Be kind of like if you're doing tug of war and it's, one person versus 3 people, but neither one can quite win out. This red line is going to spend more time and be closer to the side with 3 people on it than the one with 1 person on it. Alright, so we use electronegativities to determine the bond types. These numbers are important, make sure you get them down. So ionic bonds, values has to be between 4 and 1.6. This is almost always going to be true if you've got a metal bonded to a non-metal. It's going to be ionic. There's 1 or 2 exceptions in there, so just make sure you know these numbers. Polar covalent is when it's less than 1.7. So 1.69 all the way down to anything over 0.5. So 0.51 to 1.69. And non-polar covalent bonds is when it's at or below 0.5. So 0.5 all the way down to 0. That's your non-polar covalent bonds. So make sure you jot these down, have them, and know them for your next quiz. Okay, let's look at an example. So phosphorus and sulfur, look at the bond between those. What type of bond is it? So we're told that phosphorus has an electronegativity of 2.19 and sulfur has an electronegativity of 2.58. We need to subtract these. We always subtract the smaller one from the bigger one so that we get a positive number. You get a negative 1, you did it backwards, that's okay, just flip them, you'll be alright. So S minus P gets us 0.39. In that range from our last slide, we know that 0.39 falls between 0 and 0.5, so that phosphorus-sulfur bond is a nonpolar covalent bond type. That's all there is to it. This above one, oxygen and hydrogen, we take 3.5 minus 2.1, we had a difference of 1.4. This is an example of a polar covalent bond, one of the strongest polar covalent bonds without going ionic. Oh, wrong way. So I can get my face out of the way. There we go. Okay. So you try these. What type of bond would be formed between fluorine and iodine? Pause if you need to, then hit